So today I'm going to present my joint work on estimation, comparison, and projection of affine mortality models, similar to what Len presented before, and indeed this is our joint work together with Len, Garces, Mike Sherris, and Yoshin Zhu. So we're going to first focus on what motivates the analysis of mortality models from an age cohort perspective, and then we illustrate the data, and then we briefly touch on the continuous time mortality model and specifically the affine framework, and then we present some results and how these can be efficiently implemented in practice. So in our work, we focus on age cohort mortality data as opposed to the typical analysis which focus on age period data, because this latter type of analysis underlie the development of stochastic mortality models into the literature. And then several extensions have been proposed to account for the cohort effect which has been found in some mortality data set. However, a direct analysis on age cohort mortality data is motivated by the fact that in practice, for the actuarial application, the analysis of longevity-linked cash flows requires actually the use of cohort survival functions. And also because if we start from the age period and we extend these models to account for the cohort effect, this latter cannot be easy to identify in practice in the data. And also, another factor which make the use of the age cohort mortality models is that the cohort effect has been found to be more stable and persistent across the adult life, which makes it more convenient from a statistical analysis perspective. So the input to these mortality models is given by the estimated central mortality rates, which can be simply estimated as the ratio between the number of deaths and the central exposure at risk years. So out of this estimated central mortality rate, we can easily obtain the cohort survival function. Here we consider like a base age X, which in our application will be age 50 because we focus on retirement income solution. So out of this cohort survival function, we can easily obtain the corresponding average force of mortality, which Len has pretty much illustrated before. So the data, that's how the data set looks like. And here we illustrate the case of the US cohort survival data set of the males aged 50 onwards for the cohorts born between 1883 and 1915. And again, here we can deal only with, which is also one of the limitation of our work, we can only deal with complete cohort data sets. The reason why we focus on continuous time mortality modeling is because of their analytical tractability, in the sense that we can easily obtain closed form survival curves for the affine class. Furthermore, these models ensure consistency between the mortality dynamics and the functional form of the survival curve. The parameter estimate turned out to be more stable, this model will rely on the use of the mathematical finance techniques which can be easily grasped by the practitioners. Furthermore, this type of model turned out to fit the data reasonably well because these models lend themselves to a straightforward extension to account for multiple factors which can allow to capture the different features of the mortality surface. Within the class of continuous time mortality models, we focus on the affine class. In this, by means of this framework, we focus on a model for the intensity process for a cohort born in a certain year. And we assume that this intensity process is driven by a vector of latent factors of which is sufficient to characterize the dynamics in order to characterize the mortality model of interest. So the dynamics of these latent factors driving the intensity process is characterized by means of the following stochastic differential equation, which is characterized by mean reversion. And indeed, we have the mean reversion matrix delta, the long-term mean of the process, the diffusion matrix, and the standard Brownian motion, among the other features of this model. So a specific form for each of these vectors is sufficient to characterize the mortality law of interest. So once we specify the dynamics of the latent variables, we can obtain the survival function for here we illustrated for a newborn, but without loss of generality. This applies to any starting age, and we can observe how the cohort survival function is just an exponentially affine function of the latent variables. And indeed, once we have this survival function is characterized by two factor loadings, which indeed depend on a specific mortality dynamics for the latent variable. And therefore, out of this survival function, we can easily obtain the average force of the corresponding average force of mortality as an affine function of the latent variable. So we are now left with the task of estimating the parameters of this model, and this task is not as straightforward as the analytical formulation for the cohort survival function. So in our work, we rely on a formulation of the inferential problem in terms of a state space, where we first have the state formulation, which discretized the dynamics of the latent variable. And indeed, in this particular case, we have an autoregressive process of order 1. And here, the parameter driving this process are characterized with respect to the real-world probability measure, because when we estimate the model, we use real mortality data. And again, we characterize the average force of the measurement equation where we characterize a form for the average force of mortality, which is again an affine function of the latent variable. So, and here we outline the notation which we use for the characterization of this state space system. So in order to estimate the parameters of this model, we use a Kalman filter maximum likelihood. So first of all, the state space formulation, as we illustrated in this presentation, lends itself to the implementation of the Kalman filtering. In this way, we can obtain a closed form for the moments of the and that is for the minimum variance of the latent variable. So, and in order to speed up computation, as we did with large dimensional matrix, we use the univariate Kalman filter, where we use each element of the measurement equation, and that is for the cohort-related average force of mortality, we treat each element of this vector one by one, because otherwise we would be dealing with at least a 50-dimensional vector and related matrices, which is not really convenient, even when implemented, especially when implemented on a computer machine, because we may run into the so-called round-off error. So this is why, to turn around this issue, we use additional numerical tricks, which once implemented, it can result in a closed form for the log likelihood function, which is still highly nonlinear, and that's the reason why we use the Nelder-Mead gradient-free optimization method, but we can still estimate in a very efficient way and also in a reasonable amount of time. So all these things that we described so far can be implemented through. We implemented all these things in R, and this can be readily available through the R package Affine Mortality, which we developed again together with my other authors. And the R package Affine Mortality allows to estimate the model parameters, estimate the parameter uncertainty by means either by bootstrap or by using multiple imputation, compute goodness of fit measure to compare several models and choose the one which best fits the data and returns also reasonable projected survival curves, and which allows also to project the survival curves for future cohorts and for use in pricing and reserving in life insurance and pension applications. It can be installed and loaded in R by using the standard commands, and in this particular case, when we install the package, the package DevTools should be installed in advance. The models, so our package Affine Mortality supports several models. For this presentation, we focus on the Blackburn-Sherris model, on the arbitrage-free Nelson-Siegel model, which is quite popular within the analysis of interest rate term structure models, their generalized version, which includes additional slope and curvature factors, and the Cox-Ingersoll-Ross model. In order to showcase the wider applicability of this model, we analyzed data of 5 different countries with different mortality experiences and length of the time series of available data. So we consider the US dataset, Australia, Denmark, England and Wales, and Japan. The Japanese dataset is the shortest. It's the shortest in terms of length of the time series of available data. So when we compare all those models where we consider both the case where we have dependent and independent factor, we can say that we split our analysis between model with 3 and more than 3 factors, because those with 3 factors have been already quite extensively analyzed into the literature. And what we can see is that in most of the cases, additional factors, additional factors can return a better quality of the fit, and especially for the Cox-Ingersoll-Ross model with four factors, except for the case of England and Wales. Where we find out that the arbitrage-free generalized Nelson-Siegel model with 5 factors is better capable to fit the data. But the performance for the other models with more than 3 factors is pretty much comparable. We analyze, so other than by means of information criteria, we also look at the root mean square error, and the evidence is pretty similar. Is pretty related in the sense that additional factor return and like an improvement in the goodness of fit performance, also for pretty much all of the countries that we consider in our presentation. So as a closer inspection, we investigate the mean absolute percentage error, and here we illustrate the results for England and Wales, and we show why models with more than 3 factors perform better than models with 3 factors only. And what we can see is that the additional factors can improve the goodness of fit performance, especially at relatively much older ages. Here we are over age 95, 96, because here we can see a much smaller value for the mean absolute percentage error compared to the models with 3 factors. And also, when the framework, as we analyze, can also allow to spot a period effect by analyzing the standardized residuals. And what we can see in these diagonal lines is the presence of, at least for the England and Wales dataset, is the presence of 3 period effects. One corresponding with the Spanish flu pandemic, another one in correspondence of the Second World War, and finally the last one in correspondence of the improvement in the mortality improvement trends which occurred after 1970, and which has been found in quite several mortality experiences into the literature and also in our analysis. So when it comes to projection, if we want to project 8 years ahead, we want to produce at 8 cohort years ahead optimal forecast. What we need to do is to project the value of the latent variable, and we project this with respect to the last available analyzed cohort. And in order to do this, we use the model for the model where we discretize the dynamics of the latent variable. So we project for h years ahead the latent variable at the value for which we had for the last cohort, and so we obtain the h year ahead optimal forecast of the cohort survival curve. And this can be implemented in affine mortality through the function affine project. We compare also the out-of-sample performance of each of the models for each cohort, for each of the models and for each cohort. And once again, we can observe how models with more than 3 factors can outperforms the models outperform the models with 3 factors despite in spite of their additional complexity, except of the Japan. And the other striking evidence is how models with Gaussian dynamics, such as the AFNS models, can outperform models like the Coxinger-Sollen-Ross model, which does not have which doesn't have a Gaussian distribution for the latent dynamics, which is analytically less easy to deal with. And also, we can see how for the Danish dataset, pretty much most of the models have a projected survival curve which is pretty much close with respect to the empirically observed one. And once again, we can observe how the performance at up to age 85 is pretty much within the percentage error is quite negligible, at least until age 85, but well, at least age 85, and a similar thing is observed up to age 95 too for pretty much all of the model, except for pretty much all of the model, and which is within within 10%. So in conclusion, among the highlights of this presentation, we find out that the maximum likelihood estimator with univariate Kalman filter provides a stable and robust method for parameter estimation. All this machinery can be efficiently implemented within the R package Affine Mortality. And in terms of goodness of fit quality of the model, we find out that the Coxinger-Sollen-Ross model is capable to best fit historical data for most of the countries, especially at very old ages. And so we can also spot the presence of period effect, which can require additional modeling assumption to enhance the quality, the goodness of fit quality of the model in order to capture period effects. And also, simpler and easier to track analytically, Gaussian models provide a reasonable means to project future survival curve. And we haven't shown this in our presentation, but we also find out that all of the models turned out to be robust with respect to the range of cohorts used for estimation, which means that if we tend to exclude much older cohorts in order to consider only most recent data, the quality of the fit is, the fitting quality of each of those models is not going to be significantly affected. So thank you very much for your attention, and here are a couple of references of the work I refer in this presentation.
Thank you. There is no questions online. Is there any questions in the room? And just a reminder, those people joining us virtually, if you've got any questions, please make sure you put them into the app.
Yeah, so thanks for your talk. I was wondering, which part of your model is it that kind of means that you can only use complete data? Is it because you focus on this average intensity, like the instantaneous intensity, or where does this come from?
The fact that we cannot fit in complete cohort data, you mean?
Yes.
The problem is that the fitting, like when we implement the models, the results are really weird. Like we have survival curves which to us are not reasonable. Like too much high survival probability at very old ages, which to us at the moment do not make much sense.
Okay, so is there any theoretical reason why it shouldn't work, or is it only empirically that you find that?
No, it's only empirically in terms of computational aspects.
Okay.
Also because the problem when dealing with this type of models is that the log likelihood function is highly nonlinear. It has multiple optima, and we have to try to estimate the model using several starting values. So, and to use the, let's say, so the problem when for incomplete cohort data set can be either be given by the fact that we have to use multiple starting values and you know, this can be quite inefficient from a practical perspective. And also, for the opposite reason, when we use complete cohort, the results are quite robust no matter the starting values that we use when implementing the models.
Okay, thanks.
Any other questions? And any questions for anyone, any of our speakers?
Yeah, thank you for the talk. I think you're dealing with a very difficult topic. It's quite technical to manage these affine models and fitting mortality. I'm a bit curious about the link to the other type of mortality modeling based on Licata, for example. And you had a slide where you showed that how to project mortality rates, and that you basically had a percentage decline in the mortality curves, as far as I could see your formula, which was age independent. Is that correct on one of your slides?
Yeah, okay. So the projection in this case is, yes, it's age independent because we just project the value for the latent variable. So the latent variable, so the latent factor has affects the whole survival curve at all ages. Yeah. Okay, so the relationship between the survival curve and the mortality rates at each age is driven by the factor loading. And I cannot project anymore.
Yeah, okay, but yeah, I think I got it. Then my question is, when you fit the Licata model, there is a parameter, beta, which kind of says that there is a percentage decline, but it varies by age, and maybe by older ages you have a less a smaller decline percentage-wise than at younger ages, and that beta parameter is quite significant. So, so I'm curious about, it's important in the Licata model, and is it important in your world, and how can you implement that?
The problem is, the thing is that there's not a specific relationship between our mortality model, between the mortality models as we did in this presentation and the Licata. But Mike Sherris.
KT, that's our XT, and then you've got your B, that's our B. So our structure is like factors with factor loadings. So if you think of Licata, if it was generalised age period cohort where you had multiple period factors, right, then you've got multiple KTs, well they're our XTs, latent factors, weighted by age modulating factors, the beta things, they're our Bs. Right, so it's the same structure. Now, Licata is log rates and then all that stuff with Gaussian errors and random walk usually for the factors. Right, so our model here, the Gaussian models, we're not logging it, and we've got an autoregression on the, and if you look empirically at mortality rates, you see this autoregressive behaviour, not the random walk. But otherwise it's factors, random factors. In Licata, traditionally one factor, weighted by factor loadings, which age modulate the factor, our Bs, and then of course we've got the A factor, but it's basically the same structure except Licata's operating on log rates, right? We're operating on, in Cox-Ingersoll-Ross, we've got gamma rates, which mean, that's why they fit better, CIR models generally. But Gaussian do quite well because central limit theorem, if you've got a large population, then your errors are, okay, they're closer to gamma, right, like CIR, but normal does a reasonably good job. That's why we see the Gaussian models with 3 and 4 factors doing well. You can't do a 1-factor model. You need 3 or 4 factors to capture older age variation. But it's the same thing. It's all modulated by the factor loadings. So in the Licata setting, they're using KTs, well, they're latent factors, multiplied by Bs, well, they're factor loadings, and that's the equivalent. So it's same, it's the same, only different.
Any other questions?